Good afternoon. Myself Anil Kumar, again present for this is your today's fourth lecture, and today rather we have fifth lecture also. So today we have two sessions in machine learning to deep learning. So first session I'm taking that is already listed on the screen. The title of this today's session is methods in machine learning. So this can be supervised, unsupervised, reinforced learning, or maybe semi-supervised also. So on these subtopics, we'll focus on the today's lecture. So thank you again for joining this session. Some of the people, those who have not registered, they can log in on EduSet YouTube channel also. So coming to the learning methods which we adopt in machine learning. So these are mainly you will see in the literature from the very few past decades. The two were very well known. One was supervised and unsupervised method. And the moment you talk and you read on deep learning methods, so there you will see two more learning methods. One is semi-supervised and second is reinforced learning. So with this, there are four methods according to which we can train the algorithm to work as per our own application. So first, I'm taking about say supervised method. So in supervised method, like a supervised class in a teacher. So supervised method, you can understand like a supervised class in a school. So in a school, one class is going. So there you have few students and there is one teacher in the class. So that class, we can say it is supervised class in a school. So say here the information, whatever is information provided by the teacher, according to that information, the student learns. The student may be speaking some information content, or he may be writing on the board, or nowadays showing the LCD PPTs. So that is also all possible. So all these methods the teacher is adopting to give information to the student, and that way we can see this supervised type of learning. Same way, when we provide the training data to the algorithm, basically the application of training data is to calculate algorithm parameters. So once we provide the training data, it has a few samples of each class as well as labels. And based on this training data, we calculate some of the parameters of the algorithm. And once these parameters are calculated, algorithm is ready to be used maybe for classification or for prediction purpose. So label also comes from the training data. So classified output are called as classes gets labeled. So here you can see the classified output is basically having the class labels. So here this approach is called classification. So here in the output, once you have the label also for each class, so the output is called as a classification output. So here there's a one difference terminology. For supervised, the output is called classified output. That means in that output we have classes and that classes has labels. In the case of remote sensing, if you are generating the output, we may have label for few pixels, like in this case, a few pixels may have label of water, few pixel may have label of forest, few pixel may have label of urban and so forth. So this is a supervised output. Second is classification methods using statistical algorithm. Now, if you just see with the conventional long back, people have already well established the statistical algorithm, which I talked in my previous lecture also. The well-established algorithm are minimum distance classifier, then Mahalanobis distance, then parallelopiped box classifier, or maximum likelihood classifier. So with these classifiers, if we see, they can be used as supervised, which I mentioned in my previous lecture, and we can provide the basically training data to these algorithms to work as supervised. So here what happens when we provide the training data, they calculate the few parameters of the algorithm, and these parameters, if you see, mainly few parameters already listed here. They generate mean parameter from each class. They can generate variance covariance. They can generate standard deviation, minimum or maximum value in the training data. So if you are using, for example, C-means algorithm for the minimum distance, it is using only mean parameter. If you are using Mahalanobis distance, then it uses mean and variance covariance. Secondly, if you are using Palopide or box classifier, that classifier can use mean and standard deviation, or that can also use minimum and maximum parameter to create the box. For maximum likelihood classifier, as per the literature, you can use mean and the variance covariance if you are using Mahalanobis distance, and if you are using Euclidean distance, then it will use only mean. So you can understand here the use of training data is we have to generate a few parameters of the algorithm so that algorithm can work and do the classification or the prediction operation. Here you have to understand one thing: mean parameter does not represent the each training sample. So once you generate the mean parameter, what happens? The actual training sample representation goes off. So due to this, you can see some issues may come across. So points to consider while collecting the training data. So here we have to see one more thing. When we collect the training data, we have to consider a few points. So few points are the training sample are to be well distributed. So this we can take care when we go to ground. We can take care that from different locations we collect the samples for each class. So that means our samples are well distributed. There is no issue in this to make the sample to be well distributed in the study area. Second is training sample should represent truly to the class. So this we can take care if this area is for wheat fields. So we can take care the samples what we have collected, they belongs to wheat fields. The third criteria what we consider while collecting the samples, our training sample should be homogeneous. In the context of image, if you see this area is represented by an image for wheat field, and if you see the DN values, they are not same. So all these values which are representing to wheat, they are not same. And then here you can conclude that your samples are not following the homogeneous rule, but they are heterogeneous samples. So this point is quite difficult in the ground to make that your samples are homogeneous, specifically when you are generating samples for from an image, from the remote sensing image, your samples are hardly homogeneous. And due to this, what happens? The output accuracy drops. So here so the question is, we should continue to use the mean from the training data in the few algorithm like C-means or maximum likelihood classifier or even the box classifier, and in the upcoming classifiers like fuzzy based classifiers and other classifiers where it is using the mean parameter, or we should use the individual samples in the classifier. So that is a question mark. So if we can use individual samples in place of mean, so then what can happen? This heterogeneity can be taken care, which is coming from the samples we have collected for a particular class. So here, we have to modify the C-means algorithm, and we have already proposed last year its modified version. In place of C-means, we have given modified to C-ISM. ISM means individual sample as mean approach. That means we have made individual sample as mean. So each sample is behaving like mean in C-ISM approach. So here, once we do that, the heterogeneity within class can be considered by each sample impact, and this is not seen in the machine learning algorithms which are using the mean parameter as it has been implemented in the literature. So here, if we go for individual sample as mean approach, so what can happen here? In place of just getting one mean from these samples, all samples are behaving like mean. So if my unknown data is here, then what will happen? This will give the smallest distance with respect to this sample, even though if you calculate the distance with respect to this sample, it will give very large. But now here, this sample is very close to this one, and this will be classified to the same class. If you see with respect to mean, it is maintaining very large distance compared to this sample. So this can be taken care. You have a basically localized mean at different areas in a given sample data of a class. So with this, you can see before going further, very unique output we have experimented in a Banasthali region for temporal data to map the mustard crop. And this was the sampled field which has been mapped using individual sample approach for mustard crop. It has came very homogeneously, and same field if you see here, while using the mean parameter as a statistical approach, this sample is not so much homogeneous, and we can see other patches of mustard which are not so much homogeneous, but here you can see this field has been mapped so homogeneously on the output. So this is the effect we can see when we are using individual sample approach from the training data in place of using the statistical parameter from the training data. We have also tried a number of times if you are working with ANN and CNN and RNN deep learning models. I have mentioned that these models require large training data, and number of times from remote sensing images, it is not possible to generate the large training data samples, but these training samples cannot be generated always from remote sensing data, because we get a limited fields as a test or as a training field, and from that we get maybe 30, 40 or 100 pixels. That may not be sufficient to train these ANN or deep learning models. So what we have done, we have gone for conditional extension of training samples. So once we collect the limited samples from for a class from a given data, and we can generate the conditional information from this training data or this sample. Suppose the samples are just 40 to 60 numbers as a seed samples. So we can generate from the seed samples, we can generate the conditional information, and using this conditional information, we can extend the number of points in the same region. So here you can see with respect to blue dot, we are getting more red dot also, and these red dots are extra points which has been generated, and once you add both from seed samples, once you add the extended samples, you get large number of training samples. So here you can see we have tried from 40 to 60 samples, we can generate 3,000 to 30,000 or more large number of samples we can create, and this helps to train the CNN model. Next training approach is unsupervised method. So here in unsupervised, like there is no teacher in a class. So here in number of times if you see in a class there is no teacher, teacher has given some tutorial questions. Now that questions has to be solved by the student by themselves. So here the students have to learn by themselves. So there is no teacher support to learn. So here what happens, initially algorithm parameters are assumed. So if you compare the class unsupervised class with a algorithm which is working as an unsupervised algorithm. So here algorithm has to initialize these parameters. That means how we can initialize, the algorithm has to assume these parameters. So parameters should be simple ones like mean. So you cannot take very complicated parameters to be assumed, because later we have to refine these samples. So when we are assuming the samples to start the algorithm as unsupervised, we should consider that algorithm uses the simple parameters like mean. And that's why in statistical algorithm, you see only C means algorithm has been used for unsupervised, not maximum likelihood classifier. So that way we should take care that the algorithm parameters are simple, because we have to refine these parameters with respect to iterations. And here, if you see in the training data, labels in output are not there, because from the training data, we are not getting the labels. We can simply say it is C1, C2, and so forth, right? So here labels in outputs are not there. So here through iteration, training parameters are refined. So whatever training parameters like mean has been assumed, that mean value has to be refined using the iterative process. And this approach is called clustering. So when we go for unsupervised classification approach, this is called clustering. So here in the output, the label will be missing. We can simply say cluster 1, cluster 2, so forth, or class 1, class 2, class 3. The application of unsupervised method you can think about in remote sensing domain. Basically, we apply the unsupervised approach once we have the image of an area where I'm not aware about the area, what different classes are present. So applying this unsupervised clustering approach, we can try to guess how many maximum number of classes we can extract from this given image for this unknown study area. So that helps to guess how many maximum classes we can extract from this image. Or if we have some very discrete output and we want to group them into few clusters, so there we can use unsupervised method to divide the data into few number of clusters where we are not interested much on labels. We want to just divide the data with some criteria. So that way there we can use unsupervised method. Next is semi-supervised. There can be situation when we have very small labeled data and a large number of unlabeled data. So if this is the situation, because getting the labeled data from the ground, it required time and cost. So if the area is very large, we can collect the small labeled data with very high accuracy, and we can have very large number of unlabeled data. So if this is the situation, we can go for semi-supervised method. So here initial algorithm parameters are calculated using small labeled data, and later it has to be refined with iterative process. So once we initialize the parameters with the small labeled data, these parameters are further refined through iteration, and then here we can say this is the case of semi-supervised. Fourth case, once the deep learning people moved from machine learning to deep learning, so one more word also came in the literature called reinforced method. So reinforced learning is an area of machine learning in the absence of training data set. So here main conventional training data is not present. Basically, it is bound to learn from its experience. So we can say we may have initial seed some training data, and it can go on moving further to create the experiences, and from that experience algorithm is bound to learn. For example, as is follows, we have an agent and a reward, so with many hurdles in between. So we have an agent, we have a reward, maybe plus or minus, and with many hurdles in between. So agent is supposed to find the best possible path to reach the reward. So once he get the best possible path, he get a positive reward. And if he's going to a wrong path, then he get a negative reward. So there is reward like a prize and punishment is there. So as per the movement, the prize or punishment is given to the agent while he's crossing the different hurdles to achieve the goal. So reinforced method, if you see main points in reinforced method or learning, the input should be initial state from which the model will start. So there is a initial state from which the model will start for learning. So there are many possible output as there are variety of solution to a particular problem. So in the life also you can see there are different type of solutions for one problem. So the training data is based upon the input. So here, whatever input we provide, the training data is dependent on that. The model will return a state and the user will decide to reward or punish the model based on its output. The model keeps continuous to learn. So based on this reward and punishment, the model learns continuously, and the best solution is decided based on the maximum reward. Right? The simple words, the output depends on the state of the current input, and the next input depends on the output of the previous input. So it is like a continuous iterative process with respect to events or input and output is going on. The first output depends on the state of the current input, and the next input depends on the output of the previous input. So this way the reinforced method goes on. Coming to basic remote sensing image classification approaches. You can have supervised or unsupervised, which I've already covered just now. So here, if you are providing the training data for different classes like water, agriculture, and rock. So here, if you apply the samples, you can get the classified output. And here you can see the labels are present for different classes on your output. So this is supervised learning. Second case can be unsupervised. You have the same image of 3-band and you apply the some unsupervised classifier, and this gives you output as cluster 1, cluster 2, cluster 3, cluster 4. So here labels are missing. And algorithm iterate number of times to refine the parameters which were assumed initially to start the algorithm. Next is here hard and soft classification. The soft number of times people talked about around 20 years back initially as subpixel classification. So here you can see for hard classification, if it is a 5-band image, this can be supervised or unsupervised. So whatever method we are using, it does not matter. This is supervised or unsupervised. So here, if you see output, whole pixel is labeled to one class. This is labeled to class water, and this is labeled to class vegetation. This is labeled to wetland, and this is labeled to soil. So here we assume that our all pixels are pure pixel. So there is no mixed pixels. In this case, here if you can see that it is soft classification. Once we know that we have mixed pixels, we'll talk about later in the coming topics about pure and mixed pixels. Anyway, here you can understand mixed pixel means it is having more than one class. So here in this image, it can be again 5-band image, and we can go for supervised or unsupervised. But once we apply the soft output or say subpixel output, or classification approach, the output is not a single layer. Why? Because we assume or we feel that all these pixels are mixed pixel, or partially some are pure pixels and some are mixed pixels. So in that case, it is suggested that we should go for soft classification so that maximum information should be correctly mapped. That should be no undershoot or overshoot in the classification. Overestimation and underestimation of the information should not be there. So that is only possible when we go for soft classification, when there are mixed pixels present in the image. As a whole image is mixed pixel or few pixels are mixed pixel. So in this case, the output, if you see, it can be supervised or unsupervised. We get the here fraction images. So first image as a fraction image, which is giving membership values, that is for class water. Second is giving for class vegetation. Third is giving for wetland, and fourth is giving for soil. So here, if you see first pixel for water, it's 0.7. For second pixel, it's 0.1. Third pixel again, it's 0.1, and fourth pixel is again 0.1. So these are the membership values. 0.7 means the first pixel belongs to class water with 0.7 degree. 0.1 means 0.7. So 0.1 means in the second fraction image, that is the degree of belongingness of vegetation. The first pixel belongs to vegetation with 0.1 degree. Then third, again for wetland, the first pixel belongs to wetland with 0.1 degree membership value. And then for soil, again, here the degree of belongingness is 0.1 as soil for the first pixel. So here we can little bit give you the flavor for fuzzy approach for subpixel classification. So in the hard, what is happening, if you see this pixel, if it is a pure pixel, this is labeled as class A with membership value 1, and for other classes membership value is 0. In second case, fuzzy or soft classification, which is fuzzy is coming under the category of soft classification, assuming this is a mixed pixel. So maybe all 5 classes are mixed here. So we can extract these 5 classes as class A with 0.1 degree, class B as 0.25, class C as 0.2, class 4 as 0.4, and class E is your 0.05. So like that we can extract the class A, B, C, D, and E from a given pixel, and they are represented in the form of membership values. When we go for subpixel, you can get these representation in the form of and members. And how we get these membership values? Basically, we have to use some membership curve or membership function basically this membership curve or function, it gives you here input data here, and input data can be from minus infinity to plus infinity, and on the y-axis you have membership value from 0 to 1. So for a given input, you can get the membership value. Suppose for input 4 here, the membership value is 0, and for input 5, the membership value is 1. So this way we can generate the degree of belongingness, that is membership value for each input pixel. A few outputs I can show you with respect to the real remote sensing image. Here I'm showing you one image from Ponta image input. And here you can see the 4 classes we have extracted. One is barren land. So here the barren land is getting higher membership values. In other areas, the membership value is quite low for barren land. Here for agriculture, in these pockets, the membership values are high, and in other areas, membership value is low. For dense forest, wherever there is a dense forest, the degree of belongingness is very high, and for other areas, the degree of belongingness is quite low. For deep water, again, this is Asan Barrage. This is the area belongs to west of Dehradun near Ponta, and Dehradun Uttarakhand boundary, Himachal and Uttarakhand boundary. So here, this Asan Barrage, where you can see Asan River, Yamuna River, and Gir River. So here, when there's a deep water, the membership value is mainly tending to 1. Wherever it's shallow, the membership is maybe 0.8, 0.9, and wherever there is no water, it's tending to 0. A few issues you can see in the remote sensing images while handling the remote sensing images. The aspects can be like mixed pixels. So here you can see in this grid, these are pure pixels you can label as water. These are again pure pixels as grassland. What is the label should be given for these pixels, where some is water and some is vegetation. So these pixels are mixed pixel, and we get a question mark, and how to handle, we have to go for fuzzy classification approach. Second is number of times in the image we may have unwanted or wanted noisy pixels. How to handle these pixels, that is again a question mark. So from the literature, if you see through Markov random field or through local convolution method, we can handle these noisy pixels during classification. So if we add Markov random field function and all local convolution information in the form of a filter or a window which extract the neighbor pixel information, and using that it generates the information for the center pixel of the window, and that way it can incorporate the neighbor effect, and that way we can basically decrease these noisy pixels. So noisy pixels, you can say they are isolated pixels, like if you are mapping at 1:20,000 scale, and within the forest you get 1 pixel as water. So this single pixel, which is very small, it basically noise at 1:20,000 scale. There is no meaning to show just 1 pixel of water within that forest area. So how to handle, we have to go for Markov random field or local convolution method to add these informations as a contextual information we can add in the base classifier. Base classifier can be your MLC, C-means, or fuzzy classifier, or any other classifier that we can add, so that isolated pixels we can easily remove. So this is a case you can see while applying a DA model, DA contextual model in fuzzy C-mean, discontinued adaptive prior. So here this is discontinued adaptive prior as a contextual information we are adding. So it has 2 modes, either smoothing or DA model. Through smoothing, you can see it is not preserving the few details. Here you can see this is a dam, and there are few nearby small water bodies near to the dam, and these water bodies has not been mapped properly when we are applying the smoothing approach. But when we went for DA approach, we can see these details are properly mapped, or rather we can say they are properly preserved. The boundaries are preserved. Basically, it dissolves the boundary when it is adding the neighbor pixel information in the form of contextual. So we should see the boundaries are preserved. So that model should be chosen which takes care the boundaries are preserved. So here in the DA model, we can see the boundaries are very properly preserved. Also, you can see the one output using local convolution method in the fuzzy classifier. So here this is the raw image, and this is the classifier from that raw image for wheat class as a fraction image. And here we have applied MPCM_S. I will talk about MPCM, modified possibilistic C-mean classifier, in the coming lectures with S option for local convolution method. So here in the same image, we have added 1% noise intentionally as a pepper and salt noise. So when we have classified this image through while incorporating contextual information through local information method. So here you can see the output is quite rugged and it is quite noisy free. Same way we have went up to say 5% noise, still output was quite consistent. It was least affected by the noise of 5% salt and pepper noise. Second issue you can see in the remote sensing when you go for classification, as I mentioned in the previous lecture also, there is non-linearity. So this is one class and this is your second class, and here you have to draw a circle or elliptical shape to separate these two classes. So there is non-linear decision boundaries there, and any classifier cannot handle this non-linearity between classes. So what we have to do, we have to use some kernels which takes care of the data to higher dimensionality, and then you can see here there is a linear separation between classes. Now once there is a linear separation or linear decision boundary, any classifier can handle this separation very nicely to classify the data. Next, one more issue you can encounter specifically when you map a specific class, like when you want to map wheat from a given data. So with this is specific class, and within wheat you may see mustard is also there, and grass fields are also there, and maybe other unknown vegetation. They may give you spectral overlap. Right, from a single date image, they may give you spectral overlap. So here you can see there is a non-linear spectral overlap also between two classes. Or here you can see very nice example of spectral overlap where green is exactly lot of pixels are overlapping with the yellow pixels. So this is an example of problem of spectral overlap, how to deal when there is spectral overlap between of two or more than two classes. We have to go for temporal data. Single date data cannot handle this spectral overlap. So here you can see when you use the temporal data, this incorporates the unique stages of the crop. Maybe like here corn crop is there. So here we can incorporate the unique growth cycle or growth stages of this crop, and with that this temporal signal becomes very unique and it helps to map the specific crop. So this is all about today's first session, which I just talked about methods in machine learning, supervised, unsupervised, and reinforced learning. And I also talked about the few issues you can see in the remote sensing images and how to deal them. This can be noisy pixels or your spectral overlap or mixed pixels and so forth. And what is the solution? And here I'm ending this session. And if there are questions, let me take up. And by 4 p.m. we will start the next session where I will be talking about more focused on temporal data processing as well as the fuzzy based algorithms, mainly the fuzzy based algorithm details, and how we can incorporate these algorithms and how we can basically use the temporal data for a specific class mapping.